third talk.
Yeah.
And we do it together. So our idea is that he gets this microphone and I start with the microphone and then take over. Also us people make it.
Yes. Okay, yeah, we have two microphones.
Yeah. Yep.
Hello? Okay, welcome back, everybody. Let's start the Computing and Batch Services session for the afternoon. First up, we have Peter Wienemann, and he's going to be talking about running an HTC cluster with fully containerized jobs using HTCondor.
Hello, everybody. I'm going to present our experience in running an HTC cluster at the Physics Institute at the University of Bonn. This is a physics institute with roughly 240 members and a rather diverse collection of research fields. So on the experimental side, we have high energy physics, physics, hadron physics, detector R&D and photonics. And on the theory part, there is again HEP, but also condensed matter physics and mathematical physics. And these different research fields have quite different computational requirements. So, for example, the amount of memory required to run jobs is quite different, storage requirements are different, and also the software in use is completely different. Despite of all these different requirements, we managed to satisfy all these wishes with a common infrastructure, common HTC cluster, which we call Bonn Analysis Facility, or short BAF. And this is the network setup of our cluster. So here is the actual cluster comprising of worker nodes, which offer a bit more than 1,000 physical cores. Then we have a CephFS storage system providing roughly 500 terabytes of storage. And then in a different network, there are desktop PCs, roughly 170 at the moment, and these serve as Condor submitted hosts. The heart of the Condor system is a highly available Condor Central Manager setup by these two machines here. Then we also run a CVMFS infrastructure in order to provide, in addition to the CERN-hosted repositories, local repositories and also container images. In addition, which is not shown here, there are also two squids, in particular for the CERN-hosted repositories. And then we have a service which is called Cobalt, which is there to allow Atlas to opportunistically use our cluster. I will come to that later. So all this, the whole infrastructure is deployed using Foreman and Puppet. At the moment, there are a bit more than 300 hosts registered in Foreman. We try to recycle public Puppet code wherever possible. At the moment, we use roughly almost 1.5 million lines of Puppet code. These are modules which are freely available, mostly on GitHub. And they allow to configure all kinds of services like postfix and Crony and Apache and what have you. all modules we considered useful, we collected here on this GitHub organization. Compared to this almost 1.5 million lines of third-party code, we only had to write about 20,000 lines of Puppet code, which are profiles to customize all this to our environment. So if you compare this, this is a bit more than 1% of the Puppet code we actually had to write ourselves. Those profiles, they have parameters which we can tweak for different host groups or particular hosts. For example, this host has a German keyboard and this has an American keyboard layout and things like that. So all hosts can be easily reinstalled by just a few clicks, so quite convenient. On the file system side, we run we have three different file system types in use. For data storage, so the data to be analyzed, we run a CephFS cluster. I won't say much about this because Oliver is going to talk about this on Thursday. The key parameters are shown here. Second is we have a CVMFS infrastructure. We use that, so just squids and clients for CERN-hosted repositories, and then we also have the server part for locally hosted repositories where we provide special software, like here, for example, Mathematica, and container images which contain local tweaks, and we provide them to the worker nodes that way. We offer the software selection using LMOD modules to our users such that you can easily load the desired version of their particular software using a command like this module load and then whatever you want. The home directories are provided by a GPFS system. It's mounted via NFS. This is something we just use as customers. It's run by the central computing center of our university. Just for our convenience, we use it, what was provided there. So this is a batch system session, so that's why I also have to talk about batch system, of course. So we use HTCondor. Running on CentOS 7 hosts, and we configured HTCondor in such a way that all jobs are run inside containers. And at the moment, we provide 3 different container OSs, namely SL6, CentOS 7, and Ubuntu 18.04. The users can then choose which container OS they want for the jobs by just adding a single line like this here to their JDL file. Job submission is done from the desktop machines running Ubuntu, and due to this mixture of operating systems, development and testing is usually done in interactive containers. It's the easiest way to provide this OS variety. It's much more difficult to do that in a traditional login node approach. And then the home directories are not accessible within the jobs. This is just to decouple cluster and desktop operation, because otherwise heavy I/O on the home directories could negatively interfere with the interactive usage. So if it slows down your browser, for example. As container engine, we use Singularity, which is an engine which has been specifically designed having HPC use cases in mind. It's, for example, it allows for unprivileged users, at least in many cases, not in all cases. For example, on SL6 kernels, you still have to use it. It has to run with setuid on. So there it's not fully unprivileged. And it also offers less isolation compared to other engines, like, for example, Docker. This simplifies a bit access to special hardware. A nice feature about Singularity is that it's fully supported by HTCondor, but that's not a unique feature of Singularity. For example, you can also easily use Docker within HTCondor. There are also some items we don't like so much, namely that there is no long-term support for the community edition of Singularity, which in practice means that the operators have to update regularly to keep up to date with the with the upstream releases, and that also implies that from time to time you run into problems which slip through the quality assurance of the developers. And another thing is that, in my view, a lot of the initial motivation for Singularity is outdated, I think, because there are other container engines which run the same, which offer the same functionality and even more, and which have a larger developer and user community. So this plot here shows the number of chosen operating systems versus time, and you really see that the users actually make use of the whole spectrum of offered operating systems. In order to make our life as operators easier, and also for the users, we implemented an automatic node health checking machinery. So the idea behind is to detect what we call black holes, so malfunctioning worker nodes where jobs fail immediately, which then in turn free resources such that more jobs go to this broken worker node, and then suddenly within a short amount of time the queue is empty. So this you don't want, of course. And another reason is to detect problematic worker nodes. For example, it happens from time to time that worker nodes are heavily swapping, and so these machines are typically completely stalled, and you don't want more jobs to go to that node. And it's unfortunately at the moment it's not possible to fully control this in HTCondor. We use the start the cron functionality in HTCondor to implement that, and then we feed health information into machine ads, which look then like those examples here below. The health checks we have implemented are listed here. We check the accessibility and the fill level of various directories. We check the number of D states. We check swap usage, I/O weight, CPUs. We verify that all the necessary CVMF mounts are okay. We require a certain minimal system uptime because we don't want that jobs after you, for example, do an intervention on a machine and you reboot it, you don't want that jobs go immediately to that host. The health checks have to be finished within 10 seconds. Then we don't want nodes which have been unhealthy recently. These are all excluded in order to avoid flip-flopping. Then, of course, we don't want to run jobs on nodes which are in draining state. And then we also have the possibility to set nodes unhealthy inside Puppet if you want to do scheduled maintenance. So this shows this health machinery in action. Here again, the number of unhealthy reasons versus time. And you see that all kinds of things actually do happen. And some example reasons here, some machines have, for example, too many D states. Other machines have too high I/O weight, and another part of machines wants to reboot because of pending updates. So the users, and of course also the admins, can check the health status of the cluster using the machine ads by just issuing a condor status command with these parameters, for example. And then among the list of information which is provided is this node health, and a few of these examples are listed here below. This is an example if we operators take a machine out and to do some work in progress on that machine, for example, then this is what you see if, for example, one of the directories is too full or if the swap usage is too high. And nodes could also be scheduled for reboot, and this looks like this here. Now, coming to reboots, this is of course an important part of container security, cluster security. To keep everything secure, we rebuild the container images daily, including all bugs and security fixes. And we also install security fixes daily on the cluster nodes. And of course, some of the updates require a reboot to become effective, like kernel or systemd updates. To doing that manually is a nightmare, so therefore we automized everything. And so what we do, actually we schedule a drainage and a reboot of a node if one of the 3 conditions is met. So if the program needs restarting, reboot hint indicates that there was an update which requires a reboot. We also schedule a reboot if the uptime is larger than a month, just to get rid of cruft which piled up in the course of time. And if the kernel is older than the one specified in Puppet. In order to avoid a shortage of usable worker nodes, we spread the drainage over 10 days, such that not all worker nodes become unavailable immediately at the same time. And then we check hourly whether a node, whether the drainage is finished and it's become empty. If this is the case, we shut down HTCondor, so the node disappears from the HTCondor cluster, and then then schedule a reboot within 30 minutes. So this shows here the number of reboot reasons versus time for the cluster nodes. You here, for example, see nodes which have been up for too long, and obviously there were some long-running jobs, so the nodes couldn't reboot. So, and then just before the drainage finished, software update came in, and then suddenly much more nodes had to be rebooted for a different reason. And then obviously this job's finished, and then everything, all empty nodes were rebooted immediately. Then it was fine for some days, and then another update came in, and many nodes had to be rebooted, and here they couldn't be rebooted as fast as here because the cluster was again in use. We put all the health information together with other machine information like the location and the foreman host groups and stuff like that into the message of the day, which is shown to the admin upon login. So here this is the locational information, and here this is the health information, just that when you want to do some maintenance on the machine, you get a reminder what is going on. As I mentioned in the beginning, we also offer opportunistic use for Atlas of our cluster. So opportunistic usage means that we allow temporary usage of the resources which are not fully dedicated to Atlas alone, if the resources are not used by us. And we implemented this using a service called Cobalt and TARDIS. It's a service developed by the Karlsruhe Institute of Technology, and it allows to manage a whole variety of different resources in a unified manner. The resources can be HTC clusters, cloud resources, and also container orchestrators. If you want to have a look, you can check out these GitHub links. What Cobalt and TARDIS actually does is it books resources and then it monitors their usage. If the booked resources are well used, it books even more. And if the resources remain unused, it reduces the number of booked resources. So it's a very simple strategy, but still it works quite successfully. This is the Cobalt TARDIS setup which we run in Bonn. So there is an overlay batch system run by Gridcar in Karlsruhe, so our local tier 1 center. This overlay batch system is fed by an ArcCE. And then inside this overlay batch system, there are Atlas production jobs. On the other side, there is our local batch system. And then this Cobalt TARDIS service, it monitors both our local batch system and the overlay batch system. And then it starts so-called drones on our cluster. Drones are nothing but pilots which provide the software environment and which makes these resources available inside the overlay batch system. So this shows here the number of running Atlas production jobs in an opportunistic way on our cluster. So initially we were doing some tests with a few drones only. And then as soon as we became a bit more confident, we increased the quota, and at the moment, around 100 jobs are continuously running on our cluster, and we still have to study a bit more in detail the interference between our local usage, and then if at some point we might increase the quota even more. So then I'm summarizing. So we happily run an HTC cluster using HTCondor with fully containerized jobs. We provide software and container images using a CVMFS system, and the data using a CephFS cluster. The cluster serves really well, both for the local users and also for opportunistic usage. And what we are really looking forward to is a more powerful container solution. In particular, our dream would be a solution which would allow to checkpoint and restore containers, which would be really nice for longer running jobs and also for opportunistic usage. That's all I have.
Okay, any questions for Peter?
Oh, excuse me.
Yeah, thanks for the nice talk. Down here. He's not looking.
Ah, sorry.
So I was interested in the comment you made earlier, but maybe it's linked to your last bullet there. You said that Singularity was a great solution a while back, but maybe not the best now. So I was interested in your thoughts of what is the best solution now, and maybe does one of them solve your last bullet point?
Yeah, so one example would be Podman. The drawbacks are that it's very platform dependent. So it only works if you try to restore the container on exactly the identical platform. So these are the drawbacks at the moment, but it would be nice to make this solution more mature, such that it could be widely used. But already now, I think it would be useful, because I think many clusters, they are not completely homogeneous, maybe that we help, I think.
Thanks.
Yep, I don't understand how
Where are you?
Here, how you run your own. Did you write your own wrapper? So when Condor starts a job, the wrapper actually starts it inside a container. That's how you do it.
No, this is handled inside HTCondor. So there are flags. Other container runtimes, it's not possible at the moment. But hopefully at some point, HTCondor will support OCI. So, which is then a standard container interface. And then it might be easier to support more container runtimes inside. But maybe you will mention this topic later. Okay.
Yes, Ian. I'm here. For the users is equivalent, what they prefer?
Running bare metal or inside containers?
No,
or?
I mean there could be difference running their job inside a Singularity container or a Docker one, and even the version of Docker I was reporting this before could make the difference. So have you noticed differences in performance or even in?
No, and we haven't compared it. How the two ways to do it actually compare. So. Yeah, I have no answer to your question.
Okay. Thank you.
Here.
Yeah.
So yes, should we understand from your last bullet that you don't do preemption, you don't allow preemption?
At the moment, not.
Okay, and if a node becomes unhealthy during...
the job dies, and then I mean, then the user has to take care of it. It's the best you can do. I mean, killing it, I mean, I think it's better to hope the best and, and maybe it will survive instead of immediately killing it.
Yeah, a reason for killing it is to restore more quickly a
help.
good state of the work kernel.
Yeah, yeah, okay. I mean, for the fellow users, you mean? Yeah, that would be a reason. But at the moment.
Thank you very much for the presentation. I was just wondering, out of curiosity, so you said, if I remember correctly, that you schedule the drainage and reboot if there is a hint that it requires a reboot.
Yes.
And I was wondering whether this scheduling is dependent on how urgent the update is. So let's say that there is a...
No,
okay.
There is no intelligence,
okay.
Including urgency of the update.
Any other questions? All right, let's thank the speaker again. Dates. Todd will be speaking about updates for HTCondor.
All right. So I have been giving the what's new and what's coming up in HTCondor for 20 years now. Because 20 years ago at the first Condor Week, I was tapped to give the what's new and what's coming up. And it's been 20 years straight. I've been doing it ever since. So 20 years ago, looking back was a long time. Alta Vista was my favorite search engine, because there was no Google. Anybody remember Alta Vista? Oh, all right. I'm in good company. The J phone, I believe the J phone was just came out. It was the first phone with a camera. Imagine. I rocked my handspring visor because I was too cool to have a regular Palm Pilot. I needed a handspring. And my kids that are now graduated from college were, in kindergarten. And apparently I'm still rocking the same wardrobe from 20 years ago, which is a little scary. But so 20 years. Can anybody tell me then what year was the first Condor Week? What's that? Anybody? I heard 2000. I heard 1999, and the answer is 2000. 1999 is incorrect because there are two hard problems in computer science. There's caching, there's naming, and then there's off by one problems, right? So with Condor, we always have two release series going on in parallel. We always have the stable series, which the second number, kind of like the Linux kernel days of old before, it always just stayed the same number. The second number in the version, if it's even, that means it's a stable series. And if it's odd, that means it's our developer series. I think these are poorly named because naming is one of the hard problems in computer science. I think the stable series should be called the bug fix only series. And the development series should probably be called the new feature series because it's not like it's last night's build off the build farm. Even our development series runs in production for a minimum of 3 weeks on all the unsuspecting hundreds of users at University of Wisconsin and several other beta sites. So it's pretty hardened, even the developer series. So in the past year, there's been about 10 to 12 public releases. Condor is relatively fast moving. It's not like Docker or anything, but it's it moves along. And at any point, if you want to know what changed from version to version, there is a very detailed version history in the manual that gives a terse overview of everything. So a few years back, what new features came out in HTCondor 8.4? This one introduced the Docker job universe. So in HTCondor, that's the ability to have a program. Your job doesn't have to be an a.out that gets fork exec. Your program could be a Docker container that gets managed by Condor. We added IPv6 support, encrypted job execute directory. So when Condor writes files or transfers files on the job's behalf to a worker node, it can encrypt that data on the fly. And that's awfully nice if you, for instance, your worker node dies and in comes the Dell repair guy and he takes the whole machine and ships it off somewhere, and meanwhile the hard disk is still in that machine and it has God only knows what data on it. And we added everybody's favorite systemd support a number of years ago. I heard the groans. In 8.6. We enabled C groups by default, IPv6. We made enhancements to our Docker universe support. And we added first-class support for Singularity, which we just heard in the previous talk how that can be leveraged. So what's going on currently? What are we working on back in the Condor kitchen? Well, 20 years ago, I was reading Game of Thrones because, the third book had just come out. George R.R. Martin still isn't done with the books 20 years later. But something we're working on is getting rid of things. So there's some old cruft in Condor that winter is coming, for instance, to the SOAP API because people just weren't really using it. And we now have a Python API, which is much more popular. So out the window goes the SOAP API. We have deprecated support for RHEL and CentOS 6 because CentOS is deprecating support for CentOS 6. A bunch of stuff that probably no one in here is using is gone from 8.9. The packaging is becoming much more standardized. So like the downstream Linux distros will have the same packages soon that UW has. And this is because we got rid of things like Standard Universe, which required us to recompile glibc. Downstream distros didn't like that. And I put the HTCondor manual here. The HTCondor manual, the good news is it's very complete. The bad news, it's very complete, which means it's like 1,000-some pages. So I always joke with people that, I didn't know you could configure this, and there's a lot of configuration knobs. I always joke that, on page 790 of the manual, it talks all about that configuration knob. So now we just have a big cheat sheet called page 790, and it's basically the size of a wall, and you can just put it up. Or you can now just go to read the docs. And the HTCondor manual is no longer LaTeX-ified, but it's what the cool kids in skinny jeans like to do, which is go to readthedocs.io. Some nice things about it is you can get any version of the documentation by clicking this little button over here that says vLatest. There is a search window. Ooh, yes, you can search. Yeah. And it's also all sitting on GitHub. So this means you can, if you find something that can be improved in the manual, please click on this button, fork it, improve it, and we can merge it in. So we have a Singularity integration. We just heard a talk all about it, so I won't go into details. We've made several enhancements to our Docker support recently. When you run a Docker job in HTCondor, we monitor all kinds of usage information on the node, like the network usage and the CPU usage, just like we do for normal jobs, and that gets reported back into the job class add. A popular feature in Condor is Condor SSH to job, which allows users that are running a job to get essentially an interactive shell on the worker node where their job is running inside of either the Docker container, if it's Docker, or inside of the Singularity container. Or if it's even outside of a container, it's inside of Condor's managed area. So for instance, when the job is killed, their interactive session is killed as well. We're doing more work with interactive sessions beyond just kind of batch sessions. And this is being driven in part by things like Jupyter notebooks. Right? People want to have their notebook and have it scheduled and managed, but it's not, they don't want to sit around and wait. We've long had the ability to do Condor submit, minus interactive, and you get an interactive prompt. But we also have added some commands that help with like debugging. Like we added a command called Condor now. And the idea is, I'm testing something, I'm sitting here with an expert, I don't want to submit my job and wait for the Condor mumbo-jumbo accounting group's fair share, yada, 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 to decide if this job should run now or later. I want it to run right now. So you can do the Condor now command. Who here uses Python? About half the crowd is a Python crowd. The HTCondor Python bindings is our kind of our native API for Python folks to HTCondor, and it's become quite popular. A lot of people automate their tasks. We also released recently a new package that we call HTMap. And the HTCondor Python bindings are very steeped in the Condor ecosystem, right? There's a notion of jobs, and you submit jobs, and you get a job ID, and you query it, and whatnot. And the idea of HTMap is there's no HTCondor to learn, there aren't jobs, you're just in your native Python environment. And this work was actually inspired at a Condor Week by folks from Brookhaven Labs after we got talking with them. So here is using the HTCondor Python bindings. We create a job submit description file, much as we would with the command line tools. We use a submit object, and then we have a scheduler object, and we turn around and submit it to the scheduler, and then we can query it. But by the way, the matrix came out 20 years ago. What if you're just you don't want there to be jobs, and you don't want to know about this Condor stuff. You just have your Python program, and you want it to do work for you on the cluster. Here's an example using HTMap. So the idea is you describe a function. So this is the function that does your work. It has some input, and it returns some output. Maybe this function takes minutes or hours to run. The map function in Python, you just give it a function name, and you give it an iterator. And for every input in this input list, it'll run the function and spit out output. And this map it's just built into Python. If you do HTMap in front of it, this means run this function on worker nodes. So Condor will turn around and submit all of your input as separate jobs, run them, and then all the output just kind of comes back into your Python environment, and it's pretty slick. So we actually, when we submit the job to Condor, we cloud pickle the entire environment of the Python interpreter on the submit machine, essentially checkpoint the Python interpreter, send it across the way to the execute machine, restore that state, run the function, pickle the results, and send them back. It's kind of neat. You heard Pick yesterday talk about the annex, and we've been doing work on the Condor annex. Traditionally, it's been used to launch more worker nodes in public clouds like Amazon, but we're very interested in having an annex work well with HPC centers and supercomputers. So the building block for the annex and also for the HTCondor CE is what we call the grid universe. And this allows Condor you submit a job to Condor, and instead of it running it on a worker node, Condor can turn around and delegate that job to another queuing system, another batch system, and monitor it. So we've supported these for a while. And the new work is we've added native Slurm support, submission into Microsoft Azure, and the Cobalt scheduler for anybody who uses Argonne National Labs. And we are working on Kubernetes. We're doing some work with UCSD, and the idea is to have a CE, an HTCondor CE, that sits in front of a Kubernetes cluster. And as jobs come in through the CE, they would turn into pods running on your Kubernetes cluster. So using an annex, I guess this is a little over a year ago at NERSC, Fermi National Labs got a job, had a cluster that went up to a little over 1 million cores in support of a Nova run. That was pretty neat. And of course, Wayne's World came out 20 years ago, right? You heard Pick in Pepe's talk also talk about this. When we burst into HPCs, a unique problem is a lot of times these HPC worker nodes have no networking, either in or out of to the internet. And so we need a different way to kind of communicate and control what's going on there. And we are using the file system, because that is the one thing that by and large you can, the worker node has access to. And so the idea is when a Condor, normally a worker node would have forked and execed a job, instead of forking and execing it directly, it writes information out into some shared directory space, which then a node on the supercomputer would read, pick up, fork the job, and write the results back. So it's kind of communication through the file system. And we're testing this out in the Barcelona Supercomputing Center, and you can read about the approach at that link. So NVIDIA's GeForce 256 was considered the world's first GPU, and that came out in October of 1999. And Condor has long, had the ability to detect, manage, and schedule GPU devices. In 8.8, though, we added better monitoring in that it monitors both the GPU processor utilization and the GPU memory utilization as the job is running. It can report that into the slot or into the job ad, or both. And in 8.9, with the LIGO folks, we're working on being able to run multiple GPU jobs on one device. Because we have users that find that the GPU device is only half idle, or there's a lot of GPU memory left over. Why not run more than one GPU job at a time? We also recently got some Volta devices from NVIDIA. And if you have the newest NVIDIA devices, the Volta class, there's this thing called multi-process service, which actually provides real protection. If you have multiple different users, you could run jobs from different users on the same GPU device. So we're investigating that. We've been working with the CyTokens team to try to move away from GSI identity certificates to tokens, partially just because I have a burning hatred of certificates, and I think they're painful to use. You guys maybe agree. But I'm going to talk more about CyTokens on Thursday. We have a token authentication method added in 8.9 of Condor. So the idea is maybe you don't have SSL host certs on all your nodes or something, but you want some way, some quick and easy way to be able to have all your worker nodes authenticate themselves to the other parts of the Condor system. So the administrator can run just a command line tool to create a token, right? Users can also create tokens that represent themselves. And these are just files that they can put somewhere. So for instance, I could log into a Condor submit node as just a regular user, run a command line tool saying Condor fetch token, and it'll give a token that says whoever has this token can do whatever Todd can do. And then I could put this token in my Docker container or my Jupyter instance or what have you. We're also adding promiscuous mode. This is to help new Condor installations. So the idea is you just fire up your Condor Central Manager and tell it, for the next 30 minutes, any worker nodes that show up from this IP address range, trust them, okay? So then you boot up all your worker nodes. They go to the Central Manager. They get a token. They stash it securely on disk. And after 30 minutes, then it switches out of promiscuous mode into lockdown mode. And at that point, no new nodes can join. The USB thumb drive was first introduced in year 2000. It was $50 for 8 megs, which not quite, but it was a lot better than a floppy disk, I guess. But so we've made improvements to Condor file transfer. This is Condor has the ability, if you don't have a shared file system or don't want to melt down your shared file system, Condor can move files from the submit node to the worker node, and then when your job completes, write in from the files it created back to the submit node. And we made a bunch of improvements there. Better error messages, smarter retries, maybe performance improvements. This is something that Edgar is going to discuss later this afternoon. We also improved the way HTCondor can manage credentials, kind of part of this SciTokens work. But HTCondor can now manage credentials and retrieve them using the OAuth 2 workflow, which is supported by everybody. So as a result, we now include file transfer plugins for like Box.com and Google Drive and Microsoft OneDrive, so that users can have files either coming from the submit node or from Box.com or any combination thereof, and their output could go back to their submit node or go into Google Drive or what have you. So they can just submit jobs that look like this. My input file is sitting in Box, and before Condor starts my program on whatever node it allocates, it'll retrieve it securely out of my Box account. We always are attempting to make scalability enhancements. One that I particularly like that went into 8.8 is we call it, again, we're not great at naming things, but we call it the late materialization of jobs. And the idea is to allow people to be able to submit thousands or millions of jobs very quickly, in a couple of keystrokes, and be able to remove a batch of 1 million jobs in a couple of keystrokes. So the idea is, I'm submitting this job. I'm passing some command line argument to it that says which job number it is, and I'm queuing up 1 million of these jobs, but I'm telling Condor only materialize 50 jobs at a time, so that I'm not using all the memory and all the processing on the submit node until it's needed. So 50 jobs will show up in the queue as idle, and as soon as those jobs leave the idle state, so maybe they start running, maybe I remove them, maybe they're completed, whatever, then more jobs from the submission will just magically materialize and appear. So if you guys are familiar with Slurm, it's similar to Slurm job arrays, a little more general, but similar. So when I do this submission in Condor, I'll end up with one new job cluster that has 1 million jobs in it. And we're trying to move away from clusters of jobs to what we call sets of jobs. So a job cluster in Condor is just all the jobs that are submitted at once, at the same time. They get all grouped into a cluster. And that's great, but users really like to think of sets of jobs not as I submitted all these jobs together, but they have a higher level mental model about what they're doing. Maybe all of these jobs are my jobs that are analyzing genome 52, and then I have a whole other set of jobs that are analyzing some other genome. So what we are moving towards is the user submits the jobs, and they can tag it as part of a job set. And then Condor will do a bunch of stuff with this information. Besides the obvious operations of the user can then delete all the jobs with the same, in the same set. Condor can get aggregates on all the jobs in the set. So how many of the jobs in the set are still waiting to run? How many have completed? How much CPU time have they done? And the idea is with this aggregate information, we could even plug that back into the scheduling. So a common problem is I submit all these jobs in a set, and then I have the long tail of jobs that are waiting to finish. Maybe I could automatically have the priority of the last few jobs in the set automatically increase. And this is something we could do once we make sets a first-class citizen. The Python API is very popular, but not everybody uses Python yet. So we also are developing a REST interface. And the REST interface just runs alongside your HTCondor pool, and it's just a Flask app, and it'll lets you do things like, you can just go to a Git URL and get information about your pool in JSON format. So currently, our REST interface is read-only in version 1. So just to get status information, which is nice for dashboards and your web pages to show what's going on. Depending on demand, down the road, we may add the ability to change information and submit jobs and whatnot. But you'll have to tell me if that's something you would find useful or not. Dagman is Condor's workflow manager, directed acyclic graph manager. So if you have interdependencies between jobs. We put Dagman on a memory diet. So now Dagman can fit into skinny jeans, I guess. We actually had some users in LIGO that were submitting DAGs that had 300,000 edges, very large graphs. And we were able to reduce the memory image from like 90 gig down to 1 gig in 8.9. So some pretty drastic improvements there. We're adding the idea into Dagman of provisioner nodes. And so the idea is you have a workflow, and not only do you describe the interdependencies between your jobs, but you might have nodes in your graph to provision resources, say from Amazon or Google, right? And then once they're provisioned, then your jobs can run. And an important concept with provisioner nodes is there's an explicit deprovisioning that happens to make sure that you're not off at this conference and the clock keeps ticking on Amazon and you end up with a big bill when you get back. Because we're adding sets into HTCondor, we want to add sets into Dagman as well. We're investigating also with LIGO a data flow mode for Dagman. So the idea is if you're telling Condor all your input files and you're telling Condor your output files, right? Dagman, just when it starts up, it can look to see are the output files newer than the input files and just automatically skip that job, very much like make would do. In packaging, anybody who's used Kubernetes has probably installed Minikube, which is kind of Kubernetes all on one machine. There is now a mini Condor package as well. It's maybe a little cuter than this guy, but I don't know. So you can install mini Condor and you get kind of a complete Condor cluster just all on one machine. And this is also useful for running in a Docker container or using with Jupyter or this kind of thing. So 20 years ago, this is my favorite artifact from 20 years ago, there was the eye smell. Yes, this was a device that somebody thought there would be a big market for, and they raised over $25 million in venture capital. And this was a device you put next to your machine, and as you go to different websites, it would emit aromas like, I have no idea who thought this was a good idea, but you can read about the disaster of the eye smell on the web, and it was exactly 20 years ago. So with that, I am done.
Okay, any questions for Todd?
I have a quick one. So you said that you can, so for example, would you able to for GPUs, you would say request GPUs equals 0.3, I need half a GPU, or what is like the idea there?
Yeah, so for right now, the system administrator on the execute node can say jobs of this type, you can run X number of them. But where we're going in 8.9 is actually users would request GPU memory, and based on impact. So,
Other questions for Todd?
Yeah, thanks for the nice talk. I was interested in the HT map example that you showed, because that looks scarily like what some of our users submit. Is
Great.
that we get jobs that last for say 7 seconds, and then users submit 10,000 of these, so you have 10,000 jobs that are all trying to stop and start at the same time.
yep.
And Torque and Maui doesn't handle this very well. I was just wondering how Condor fares with masses of jobs that are starting and stopping.
A second or two, well, you're not going to get very good throughput, right? Because there's a fair amount of overhead to starting the job, and with HTMap, it has to move the state of the Python interpreter out and move it back.
I'm more worried about things surviving. Torque and Maui don't survive this very well.
I think it'll survive. I think there'll be a lot of wasted utilization, but I think it'll survive.
Other questions? All right, let's thank the speaker. Yes.
Hello, I'm Thomas from DESY, and we want to show you some of our HTCondor installation and or tell something about policies. And as some of you know that I will retire in January, we share the talk with Christoph as my young successor, who will.
How do you get the full screen? Sorry.
Thomas. Okay, our base installation. I start with the whole batch. So on the left side you see our HPC cluster, which is built on Slurm. It's one of the greatest cluster at DESY, and also this most growing cluster now. And on the right side you see 3 HTCondor clusters. It's our bird computing I'm talking about, our test cluster, and also the grid environment is completely built on Condor. And as you see, we all use parallel file systems instead of file transfer for these things. The outline of talk is that I will give some different perspectives on the system from user, administrator, and operator things, and do some words on authorization. And then Christoph will start over with our new features of GPU, Jupyter, Docker, and Outlook and conclusions. This is our main block building for the bird cluster. You see file system below, and the job flow is from left to right. On the left side, you see the red user submitting jobs on the remote scheduler, and on the central scheduler, we use our policy settings on all this stuff. And on the right side, you see a bunch of worker nodes. There are sometimes a little bit of them. There are GPU nodes, or there are standard worker nodes, or worker nodes with some Jupyter add-on on this. And on top, you see we have about 1,400 users, which are working in 25 projects. And the hardware is about on 8 cores, 500 machines, and this is about 5.5 gigabyte per core what we are using. And on the right side down, you see also something for Docker. We're still thinking about how we implement this. So we have about 500 machines, and if we just freely give it to the users, we cannot scale up if 2,200 users parallel will use a 3 gigabyte Docker image, so we are still thinking about this. So the user perspective should be very smooth and easy, because if you satisfy 90% of the users, you have only the work for the last 10%, and so we try to do a little fiddling and things, and also the user can request simple things. My job runs this time, I need memory, disk, and I want to run under my specific project. And this can be different if a user is on CMS or sometimes working for the H1 old experiment, so he can dynamically choose this project, and we do the accounting and the fair share dynamically, even for the same user. Then our default runtime, if the user doesn't wish something, is 3 hours, but they can also have 1 week runtime for a few minutes, and this all with full Kerberos and AFS credential support we supplied. As Todd said, it's made for CERN and DESY, and we hope also in the future for others. And we have also good experience with the new professional Aristo support. This is the successor of the public AFS, and it's working. And the share, of course, is proportional to the amount of ownership a user or project has, and is scheduled with 1 week history on our cluster. And it's based on some job classification I will show soon. This is a graphic you will show a few times, only there to point out some of the specialists of the special things of one of the services. So what you can see here, also on the left side, there's a submit host on the top of it, and in this case you see the user can choose my project or the default submit host this project, and the scheduler will care with its valid project and with allowed to, and is propagated to the right side to the worker node, and also makes up the share. And this is all read from with LDAP from the user registry. We made the so-called user maps from Condor, where you can have bird users, grid users, or newly grid GPU users must be also have permissions for using GPUs, and we also can define bad users or service time, so that we put jobs on hold when they come in the wrong time. That's what they do. And you also see from the coloring that who needs access to what. So you see the green user output on the right side. This has been written by the worker, and the user log itself is written by the scheduler or the shadow process, and the units also the Kerberos credentials to write in case of into the user's home directory. From the administrative point of view, we try to keep everything simple, so we have remote submit, and on the scheduler we use a lot of transform to check for policies, maximum and request runtimes in these valid projects, or otherwise we put the jobs on hold if they are not valid, and we care for the runtimes and minimum memory to make a job always running. And the features from Condor we use is periodic remove for the length of the job, runtime calculation for draining nodes is coming from HTCondor because we set the job properties properly, so HTCondor knows how long a job will need to drain. And the quota and fair share do with special mode I tell now with overcommitment. So what you see here is on the right top, all the kind of jobs for his memory and runtime we classify from light, short and long, and we use the light area, the green area and the red area byte for doing the fair share. And in case we do a combined fair share of the light short jobs and the long jobs, so what we see on the right, down on the right is that every project got 300 points or percent, and the red one are the real percent ownership, and the light jobs are overcommitted with 300%, so they can use more. And also we have an entropy in the system, so if you have 7 days jobs running, every minute, seconds, some jobs will stop and whatever. So what we reach with this, that after at least 2 or 3 hours, when the share should change because a project comes back in and has more jobs, it maximum takes 3 hours to adjust the correct fair share, even with the history of the jobs. This is an example. So when we have some overcommitment, maybe experiment owns 30% of the resource, we commit about 50%, but when the cluster is full and everybody wants to be working on his share, the Condor system reduces this to 100% proportional, so we can have a large overcommitment, but in real physics on the cluster, it uses the real ownership fair share of the current project. What we didn't achieve, what we had with the grid engine, it's not only core-based, we were still working on it, that the share value is proportional to the cores and the memory the people are using. From the operating view, we want to be independent from our operators. We as admins do not want to care for every machine of the 500. They do a very good job. And so we gave them some tools called batch node, so they can immediately take every system out of the service. And we have a request system where the system asks, because we have grid nodes, we have test nodes, we have other nodes, and if the operator says this node must be down, the system knows where a node currently resides and puts the host down. It's without preemption or job killing, without specific operator knowledge, and it's all viewed in one system. So and we have 2 examples. So there's a standard mode. The time runs from left to right. So this is what you're normally doing. So the red point 1, we stop the service, we start draining, and it takes some time depending on the jobs running on a node, and then sometimes you can have maintenance, and we have also an asynchronous downtime that nobody cares about, node not running jobs or whatever. And sometimes we can automatically reboot or whatever, so because we know the correct timing and all that stuff. So, but if you look at this, so the node will go slowly empty, and this is a loss of resources. So we decided to build up a new system that is draining without draining. So we just now at point 1 we modify the service that we only allow jobs which are short enough to end until the scheduled maintenance, and which do not belong to a project with health maintenance. So it's a little bit more complicated, but we are working on it. It will work. There, that was the basic system we are supporting, and you see now I took some hooks inside for the new ones, and they will Christoph explain now.
What's going on?
Yeah.
There it is. So,
Rechts und links.
being the successor, by the way, it is with 20 years overlap. Tell this to your human resource people. So this is some of the later development we have in the Condor pool. So the first GPUs at DESY arose in some local workstations, so they were only accessible by very few people, obviously. Then those GPUs were moved into the HPC cluster for whatever reason. But that was not too clever, so we now moved them into the HTCondor pool, and that turned out to be very easy. We just have an additional batch resource, which is called GPU, and you have to be entitled to use it by your local admin, who gives you the resource in the registry. And then you just ask for a GPU in your job, and then you will hopefully end up on a worker node with the GPU. At the moment, we have only worker nodes with one GPU, with 30-something of those. So it's, in a way, it's full node scheduling. And at the same time, the GPU slots are also available via Jupyter. So you are actually, it's actually possible to request a GPU machine using a Jupyter notebook, which people, of course, like. Well, Jupyter notebooks are mostly interactive, and people who like GPUs, they tend to like interactive work. So we currently see more interactive usage on GPU nodes than batch usage, actually. This is how this all blends into the thing. It's not so special, actually. And then, well, as we heard on the site reports, Jupyter is like popping up everywhere, and people were coming to us too with requests for Jupyter notebooks, and we, at a certain point, we decided not to be old and boring, and nobody from my colleagues is actually using actively Jupyter notebooks, but there is clearly a strong demand amongst younger peoples, and I personally know people at DESY, they literally live inside a Jupyter notebook. They use it like Google Docs. Yeah, they go into a session and then they type everything in their Jupyter notebook. And they have some neat features once you get used to it, actually. So, long story short, we decided to, to come up with a Jupyter Hub, which is actually a login host available from the net, from the internet, from everywhere. And with a web browser, you log into the Jupyter Hub. And in the background, the Jupyter Hub is starting a Condor job through the scheduler. And once the Condor job is working on the worker node, this is actually then the one slot with a Jupyter notebook in it. It connects back to the Jupyter Hub, and then the user ends up in a workgroup environment. So he will have his AFS home. He will have Kerberos tickets. He will have all the PNFS, CVMFS, everything is like it would be on a workgroup server. And of course, he's still in this little slot on the worker node. So if he wants to he wants to work on bigger amounts of data, he would probably be wise to use HTMap or to use the Python bindings to get out of this slot and submit into the pool, which is possible, of course. Currently, these slots are running 22 hours. So the idea behind it is you log in once with your notebook, and then you can work for a day, and you have to re-log in the next morning. But as the notebook is checkpointing every couple of seconds, it's no problem at all. And of course, this is running when you log out of with your web browser and go home. You re-log in, you end up in the same slot. So the notebook is running all the time. It's very unusual to stop actually a notebook actively. Even if you log out, the notebook in the background keeps on running. So we do this on CentOS 7 because we use Python 3, and currently we have a soft limit of I think it's 4 gig in the meantime, but we started with 2 gigs. And well, it is just a wild guess, so we have to see what time will tell us and what user will make out of it. And the very first beta usage will be the Beamline for School project, which is this year not at CERN because they don't have any Beam, but it's at DESY. And the first thing they requested were Jupyter notebooks, actually. So these are, I don't know if you're familiar with the Beamline for Schools. It's schools can apply to high energy physics labs for time on the Beamline for some experiments, and I think there's like 2 schools that can win the big prize and for 1 week be at the light source and do some experiments. So that's kind of handy for them, of course, because now they can they get a bit more preparation than a regular user at DESY. So they can log in forehand and check through the Jupyter notebook how the data analysis would go, and they have some example data, and it's all quite well prepared. Yeah, most of this is already said, I guess. This is how this all blends in, but again, we use the batch spawner, and this is all done quite nicely in the Jupyter Hub, and also the support in HTCondor it's all there. It's just a couple of knobs, and the only thing that there's some work left to make the error handling a bit more robust, or to implement any error handling at all. So it works really well as long as it works, but as soon as the HTCondor job with the notebook in it is not starting right away or something, then the trouble begins, and the end user will never get any message what's actually going on. It's just he's just looking at the screen, nothing is happening. And of course you want this job, the Jupyter job, to start within a couple of seconds, which is usually not a problem with HTCondor. But when you come from a test pool where you have like startup times for a couple of seconds, and then in a production pool like at DESY, which is usually very full, and we have usually like 6,000 jobs running, it's very difficult to get one of these Jupyter jobs starting in a couple of seconds. So we came up with the idea together with the Condor team to use a second negotiator and collector to do so. And this will be published on the website, I guess, in some time, how to do it. It's not a big secret either. But then you get really nice, quick startups on the Jupyter jobs without hassling with all the other stuff that the active pool is actually doing. As CentOS 8 is now on the horizon, we look at our pool, and we still have mainly Scientific Linux 6. So for quite a while I thought, oh, one day we're going to have CentOS 7, and then everything's going to be so great. The NFS client will be much better, and but now it's quite obvious that once we have CentOS 7, it will be like being in another prison, because it's going to be very old when we have it. So what we really need is we need to decouple the host OS system from the thing that the user actually sees. So and we want to use Docker to do that. And we're quite far, but we need to get the Kerberos AFS stuff running reliably in Docker, which is a bit of a hassle, and but that's going to come probably next year. Well, that's Docker, how it blends then in. So we don't plan to run any user Docker images. We only want to run our Docker images. So another project is function as a service. As you know, today everything is a service, and so colleagues from Thomas and me came up with the idea to do analysis, data analysis as a service. And the idea behind it is, I don't know if you know Dcache macaroons. That's kind of like the science token. So you get a macaroon which enables you to write or read a file in Dcache. So you can do all the storage access with a nobody job using this macaroon. And the idea behind this is when a file is written into Dcache, there's an event created, see how this works. Yeah. And then via Kafka, you get it on an authorization node and generate a macaroon. Given this, the owner of this macaroon can read this and write this for, I don't know, a day or whatnot. And then again, Kafka will forward this to some kind of function as a service provider. And there will be a Condor job created. And inside the job, there will be the macaroon and hopefully a science token or something as authorization. And then the job would automatically start through the scheduler. And once it's done, it would then write back via the macaroon into the Dcache. So for the scientists, it would mean for every job I put in this directory, automatically there will be an analysis going on, and the results will show up anytime in a certain directory. So this is the guy who's actually in charge of this. So if you are interested, you can drop him an email. And outlook and conclusions. Oh, the birds. Of course, we, as I said, we want to get this Docker stuff running to get rid of this coupling of host OS and drop OS. And we are still waiting for the full Kerberos and AFS support inside HTCondor. We will still finalize the Jupyter and GPU configuration. We try to get rid of SL6 as soon as possible. We see a lot of use of Singularity in the grid. And this could be a thing for Bird Pool 2. And we have this function as a service, as I said. And that's mainly it, Thomas.
Yeah, so the second point. Yes, this second point, so we saw the user can request runtime, and the new Condor feature does not act transparent on class ads which begin with requests. So we are lost for the new versions because there's some dependency created implicitly by Condor. So we have to talk with Todd. I will send you a mail this weekend. The other things we have solved now, the idling jobs, there were some jobs that were not propagated to the negotiator. That was a grid engine problem, as I say. We tried to configure it that weight of a job is half of the core and half of the memory, and there was a calculation to integer which ended with 0, and this was for small jobs were never negotiated. Yeah, and for our maintenance, so I would wish that we have a central node status that is not locally on the node and lost when it's reinstalled, so that we can disable a node forever on a central server. And this is a Nico event from the last HTCondor workshop, so if you're interested in our configuration, there are a lot of more details for class ads and transforms inside this talk. This is a little bit common to this, but with more technical information. So that's it, I think.
So okay, let's thank the speakers. Any questions for Christoph or Thomas?
It's good. We had a very clear message, I guess.
Yeah. I understand you.
I had a quick question. And the request runtime feature, so in Condor, that allows for better scheduling, I guess, because it knows how long the jobs are potentially going to run?
Yeah.
Okay.
That's actually super neat if you think it over, then because if you have a scheduled downtime, it's longer than until this.
But I think we will solve it because the Condor team has the same thing in mind, but with different solutions. But we will come together, I think.
Okay. Any other questions? No. Let's thank the speakers again. And next we have Edgar, who will be talking about HTCondor file transfers.
All right. So my name is Edgar. I'm at the San Diego Supercomputing Center that is located inside UCSD. I'm happy to see some of you that went to San Diego last HEPiX in March. And this is a little project of mine about testing the Condor transfer scale. So how do Condor scales, or how do the transfer system of Condor scales with different parameters? This work has been done mostly by a student, undergrad student working with me, Ilan. So if you like it a lot, well, it was all because of my good mentorship, and if it's not good, it's all because of a student work. So where did it all come from? So the GlueX experiment at JLab said that they wanted to use the Condor transfer system to transfer the output Monte Carlo of their Monte Carlo jobs back to the submit host as the rule, as opposed to the LHC's experiments. They wanted to see if they could do it. So we tell them, well, we need to parameterize this. And these were kind of the original parameters they set up. So imagine that you have 20,000 parallel running jobs. The output is somewhere between 10 and 100 megabytes per job. The input is fairly small for what you expect from Monte Carlo. And the job length becomes 8 to 9 hours. If you compute that and put it into a nice formula, you get that what they would need is this write rate, something around 55 megabytes per second from worker node to scheduler. In the grand scheme of things, that's not a big deal. So we want to see if Condor could do it. So the question is, of course, can Condor handle this? And the first question is, in a normal setup, can Condor saturate the network interface? And what I mean by a normal setup is a normal batch setup in which you're running on your own site. GlueX is a small-scale experiment, so it runs on the grid on several sites. How much CPU time is wasted on Condor transfers? So basically, when Condor notices that your job finished, it tells the starter tells and starts transferring your output file to the shadow. During that time, which you would expect that is low, that CPU or that slot cannot be negotiated and is not being used by anybody. This in Condor terminology is called post-execution time, and I guess that implies more things, but basically post-execution time mostly means transfer time. The third question for most of you would not be interesting because, of course, I guess none of you have a site in which the compute node is very far away from the submit host in terms of latency. But for grid, this is very important, right? So you could have your submit host at CERN and run at Fermilab. So what is the consistency percentage? And yes, like if under stress, how many times would you transfer the wrong file or miss a bit? How do we test this? We use a normal gliding WMS frontend originally, a scheduler and somebody running the tests. And a sleeper pool. So a sleeper pool is just an overcommitted Condor pool in which some slots are considered sleeper in the sense that you will run a job that doesn't consume CPU, memory, or disk. So it's pretty much a very lightweight. And then we just use a standard gliding WMS setup to measure this. How does a really scheduler? So we didn't want to test anything fancy because we want to make this test like good for any small to medium scale organization. So you don't need any like high-end hardware. So it was a 10 gig card, 128 memory, 24 core, and 2 SSDs plus some spindles.
So the first question is, can Condor saturate the network? Meaning, just by doing transfers, can it really fill up the network? And we did to the limit of the SSDs. We even achieved more than this. Given certain things, so this is, imagine that you're in your same site, and this is 4,000 jobs, more or less on 30 minutes, so you get like 100 and something jobs per minute finishing. You can definitely do this very well. These results are from, and the interesting question is, what is the CPU time that you lost due to transfers? I have some old results from 2017. This still that was. And the question back then, or what we did that day when we tested this with Condor 8.4, was a kind of surprising result, but I was not totally surprised. It is that at double those rates, you continuously lose CPU the farther your submit host is from their starter. Back then, I said, and this is, imagine that 0 milliseconds is San Diego, 10 milliseconds is Santa Cruz, 30 milliseconds is somewhere in Washington, 50 milliseconds is something in Fermilab, and 80 milliseconds is somewhere in BNL. If you go this far, you will end up losing a lot due to just the same file, just adding by latency. These results were in 2017. We got them in 2018 CHAP. But I didn't believe them myself. I was like, this is totally biased. Edgar doesn't know what he's doing. So during the summer of 2019, we got a scholarship for a student to work with me and to reproduce this test with new versions of Condor and actually do this correctly. Because what I was doing back then is submitting maybe 10,000 jobs, putting a limit in the max running jobs in the SCHED, and that way controlling how many jobs more or less run per second, and then controlling more or less how many jobs, what is the length time to have a certain amount of jobs finish at the same time to really stress test. Ilan work, we did something that we call it the glide tester. Basically, you bring up a bunch of pilots and have them running at the same time, but not taking any job. Once you have 500 or the number you want, you submit all the jobs at the same time, start them all at the same time. Since you control how long they run for, then they all finish at the same time. And of course, we want to test this with new versions of Condor 8.8 and 8.9. And we want to add transfer consistency, meaning checksumming. The results, and this would not be a high energy physics if we didn't put a plot and a fit. So it still fit pretty linearly, latency and post-execution time. In the red line is 8.9, and in the blue line is 8.8. We still see how much time you lose or you waste the further away your submit host is from your compute host. Some hypotheses. If you think how Condor works, and Ilan was very good, he went and looked at the Condor code. And not to bother you, the shadow process that you see actually starts several threads. And under this a specific situation of high concurrency and high latency, you could end up with a race condition in which a socket gets closed, and but the shadow thread dies, but is not known by there has a shadow reaper, a shadow thread executioner there, and they don't know. It started again, and it fails because the other one is still alive. The real question is, why are those TCP sockets being closed under this condition of higher latency and high concurrency? You see them in the log. You see these connections here. And you see the only thing you see in the starter log is a shadow exception. other hypotheses that are possible is that the way we add the artificial latency, because all those tests are of course done in San Diego, is by the DESY command. So we say everything coming in this interface adds some latency. It turns out that Condor, even for daemons in the same machine, uses sometimes the public IP. Even though, so we could be adding latency to daemons talking on the same machine, which of course was a case that in practice never happens. So if you got any idea of how I can add latency without adding, but somehow filtering, not adding latency from same IP, I'll be happy to hear what you have to tell me. So how does anyone know how to add latency but only IP based? Some conclusions. At the proposed rates, GlueX will efficiently, and is right now using it, this was in 2000 and 2019, they have run all their Monte Carlo this way, no problems. It also holds true if you double the rates, but maybe not much further than that. Latency greatly influences the efficiency of the Condor transfer mechanism. I would put this in quotes because we see that it influences it, but we haven't done the study of mining the data of real transfers, not this generated. This as an experiment, and we haven't seen the data from other folks. Interesting, even under high stress, we did these MD5 sums. Condor never missed a single checksum on a file, meaning that it never transferred the wrong file, or if it transferred, it always matched the checksum. And to answer Jeff's question, you can have 1,000 jobs finished in a second. Very quick jobs, transferring files. Condor will hold it. Some future work. This is from my colleague Brian Bockelman. If you think about this plot, really what this is only telling you is that Condor transfers are sensible to latency. It doesn't tell you that if the other transfers would be even worse. So we want to do the same thing with HTTP transfers. Unfortunately, we had to come up with our own HTTP because Condor HTTP transfers are good for input transfers, so they support HTTP transfers, but in input, not for output. So we had to come out with our own, basically our own web server that as a put can bring a file and store it in the same machine to compare. I had preliminary data here, but I didn't want to check it because I haven't time to really look if it matches what I was thinking. So I was not good with posting it here. Interesting, one of the LIGOS framework, Bayes waves, for the next run, they calculated they want to use this same thing. They also use the Condor transfer mechanism to transfer their output. And the numbers they are talking is saturating something over a 40 gigabit link. So this will definitely have to be fixed by then. Some acknowledgements. Of course, the Condor dev team, they have looked very carefully at all our attentions. They were very fast at answering email and worked with our logs and what we could do. They are very eager to fix things, and they like these tests. The different funding agencies that fund my work and Ilan's work. The UCSD Physics Division for the summer grant for Ilan, and the Tier 2 admins that they provide the infrastructure to these tests. And now I take some questions.
Okay, any questions for Edgar?
All clear.
All right, let's thank the speaker again. And now we have the coffee break.